Thank you very much. So this talk will be about how we went from like doing on-device fuzzing testing in a company called Qualcomm to like build like a full emulated phone from existing pieces in an Android project, and then go towards GPU fuzzing and get some interesting results. So I will very briefly go through my presentation since I've already been introduced. So I'm Romain Malmain, I live in the south of France, PhD student at Qualcomm. This is the work I've been doing in Qualcomm for 3 months this summer, and I've been under the supervision of Scott Bauer that has been technically helping me with some like internal stuff, and then with whom I've been discussing a lot, especially to get this talk like open sourced, which has been a lot of work actually, because of bureaucratic reasons, let's say, but here I am, so I'm very glad we can actually show it to the world because I think it can be helpful. So, where are we going? I guess you already seen this figure a lot in the past already. The complex layers in Android, from kernels until libraries, user applications. So I've seen yesterday that it's around 2 million lines of code nowadays, but I believe it's much more than that. Like Android goes way beyond the kernel plus user and applications. There is also a bootloader, boot ROM. You can also find some basement stuff, like all the trusted world with services, another kernel, and all these things like interact together all the time when you are using your phone. So that makes a very interesting attack surface that can be approached from multiple angles. There is also this figure. This is the most up-to-date I've found so far that kind of gives the amount of vulnerability problems among like multiple chip manufacturers. See them here. It's not like always growing. It's kind of there are some variations, but be careful because like this is just about the report. So of course, in the past there was less activity around that. So it doesn't mean there were less bugs, just that it was less looked at. Another thing you may have seen in the past, 101 fuzzing slide. I will not spend too much time on this today, sorry about this, but I will try to make it understandable. So usually you have 2 parts, the fuzzer and the target. The fuzzer is what you can see on the left. On the middle you have the target function that you want to test. On the right I've just put a CFG that basically represents the control flow of the function you've seen there. The fuzzer will just send an input called X here, that will go through one of the paths. Here, the X is 1, 2, 3, 4, so it will just go through the condition. It will do something here, I plus 3 equals 5, and then you have the return stuff. Fuzzing is mostly used to find bugs. Here, there is a bug that you will most likely be able to see. I've put below the coverage map, so this is basically what the fuzzer will receive once the input has been executed, so that the fuzzer can understand, or I mean, understand is not really the best word to describe that, but at least to have a view on what's happening in the target. And then the fuzzer can mutate it. There are many other pieces in a fuzzer. It's just like to give an idea. So, I mean, this is just the basic loop of a fuzzer. And then once the mutator is there, it will change the input, let's say, bring another input X, test it again, and you get the idea. It just does this as fast as possible and try to exploit the program as efficiently as possible. Okay, I've talked about on-device testing before. On-device testing, what does it mean exactly? It just means that you have a phone that you put somewhere in your lab. You put your target in there, and then you let it run forever. You can have these beautiful farms. This one I found online with I don't know, 100 of phones. You just put the target, bring inputs, just like we've seen before, and then you see if you can crash this. But it's not a perfect world, especially because, as you can see, it's not very scalable, at least if you don't have billions of euros to spend. Let's say, you will need to have 1 device per fuzzing unit, and then you buy many phones if you want to have good execution speed. It can get quite expensive, especially if you need to update the hardware. if you go to some chip manufacturer company, they need to usually update the hardware very quickly and frequently to fix bugs or have better performance. And then, of course, you will need to most likely update these test phones and then update new targets so that you can get the latest bugs. Debugging can be quite hard, especially because once the phone crashes, usually you don't really have a choice. You will need to reboot the phone. If you do it correctly, you can have some kind of setup to do it automatically, but sometimes you will also have to do it manually because everything cannot be covered. And rebooting a phone is quite slow, so if you have a lot of crashes to handle or some issues, it can be quite problematic. I didn't put it there. There is also the statefulness of the target that can be problematic also, but you get the idea. They are full of side effects that can affect the performance of the fuzzer. So this is why we were trying to build something around emulation. Emulation is basically a way to rebuild the phone you have on device, so your real phone, and then port it into a computer and kind of reproduce how the phone works, but in normal software. So you can imagine this phone with a lot of devices, Wi-Fi, baseband, everything. And then you will just basically create one C file, or any programming language. It works perfectly well as well. And then you will have to describe how these components work so that you can have an environment that is as close as possible to the real device. And then get this final executable that will serve as the emulator. Usually it's a lot of work, because you will need to handle a lot of problems, especially everything that is related to concurrency, interrupts. Phones are, as I said before, very complex, which makes also emulation as complex. Fortunately, I'm not alone. Some people have already worked a lot to get Android stuff working on the computers. There are multiple choices there, but the most recent one I found was Cuttlefish. Cuttlefish is the successor of Goldfish. They basically try to get emulation, or in their case, virtualization working for Android phones without having to change QEMU. Goldfish used to have a different fork of QEMU with patches above. What they did is to basically have QEMU, which is a generic emulator, and then just have it working without having to change anything. This is how it looks like in some artist view, let's say. It's missing a lot of things, and can not be so easy to read, but you can just remember that there is this Android VM that communicates with some devices in QEMU. So QEMU has an implementation per device that will be helpful to get the VM working correctly. And will also communicate with another process called Cuttlefish that will do some other tasks I will not really describe there, but just remember Cuttlefish is kind of driving QEMU. It can also be cross-VM, but here I work with QEMU, so I just kept this option. And then we'll do some very useful things get some disk layers that of course I cannot describe there, but just remember this is just to get a memory for your VM and get the right command line to feed to QEMU. If you already use QEMU, maybe you've seen this gigantic CLI with billions of parameters. They can be quite complex. But Cuttlefish does everything for us, so makes it much easier to use. So what Cuttlefish is based on is this virtual board called the ARM Virt board. I will refer to it a lot. It's basically a simple board for R64 that has this Cortex A57, some RAM, UART device, RTC device. So a bit of everything with kind of generic devices that can be used to then build a correct VM above. This is a representation of the address space of this virtual board. So you will have the flash at the beginning of the address space, and then the more you go, and the more you will find some other devices like the GIC, which is the interrupt controller. You will have the UART device I mentioned before, et cetera, until you arrive to the PCI Express. And this is basically where the Android virtual machine will live, and then we interact to get its activity running. So the plan was basically to get Qualcomm GPU kernel driver in QEMU working. So we starting from there, how basically we get the Snapdragon stuff running correctly, which involves a lot of let's say steps in the middle, like getting to get their Android kernel to boot, which is not exactly the like generic Android kernel. Implement the QEMU devices, of course, that are present in the Snapdragon that are at least necessary to get everything running until the GPU, and then start to interact with the kernel driver. Because we want to basically fuzz this kernel driver, we will want it to run in a somewhat correct state, and then interact from user land with this kernel driver and see if we can find interesting things. Then the second part of the plan is to get this QEMU thing running and merge it with another thing called LibAFL QEMU, which is a project that maintains a custom fork of QEMU that we use a lot to do like quick fuzzing. Like everything is embedded in a single process. So if we can get the QEMU stuff working correctly with the Snapdragon board, then we can just merge them together somehow and then plug them with the fuzzer, and then we fall back to the thing I was presenting at the beginning with fuzzing 101. We get this kind of loop running, and then we can just see what happens. Okay, that sounds simple because like you could think maybe that everything is there, Cuttlefish is working, LibAFL QEMU is running, so well, what's missing? We just have to do the single device and then see what happens. Unfortunately, it's not that simple. I will first describe what a device tree is to let you understand the problem better. The device tree is basically a way to represent the hardware on which the kernel is running. So this is, you can imagine it as like a binary blob that will contain all the devices running on the device that the kernel can read, or the bootloader, and then see like what is present on the board. You will see that each node in this device tree represents a device most of the time. They are connected together, and they represent which device is held by which device. They have some things called properties that basically describe which MMIO range are like present, which interrupt line is necessary, what are the links between the devices. And then we find the DTB, which is basically taking this device tree, compiling it until this device tree binary that can then be parsed again by the kernel when it's injected in the virtual machine. This is the DTB visualization of the board used in Cuttlefish, the ARMVIT board I've mentioned before. So you will find back all the devices I've presented with the PL011 and such things. You see, it's just a way to represent it. FDTV is the name of the tool I've used to do that. You will see some white edges that are like basically representing the parent-chip relationship. And then the grid edge, which is basically representing a pointer from one device to another. So if you see a green edge, it means that one device is somehow connected to the other device and can refer to it to describe how they like relate together. So this is basically how this device tree binary is used. This is like the address space and the register. So this is basically the representation of the virtual machine I've described before. Address space is the same as before, and the registers are basically the register used in the virtual machine. And then what will happen is that the QEMU virtual board code, so this is done before the virtual machine boots. It's basically done during initialization. It will be copied into the RAM of the VM. Then it will go through some parsing in the bootloader. So the bootloader knows where to find this thing. This is what I've put in the thing on the right. This is a specification of the virtual machine, and say, oh, you will find this DTB at address 4 or something. So the bootloader knows it has to look at that. It will then parse this thing and write the address to this blob into register X0, because Linux wants to get this address at X0 so that it can also parse this DTB. So Linux will know that once the bootloader is over, it will read this X0 register, and then it will be able to do the parsing of the DTB as well. Usually, both the bootloader and the kernel does this thing because they need to know exactly how to use that. But just remember that there is this kind of like passing around between the two programs to know what to do with this with DTB. And then you have the end of the boot that you maybe are more familiar with, like the PID1 init process that gives the hand to the init scripts, and then finally goes to whatever program you want to run in the VM, which for us would be the fuzzing target, so the GPU userland program to communicate with the kernel driver. But this is where the problems happen and why it is not as easy as it could sound. First, you will have to handle both the ARM board, but also the Snapdragon address space. Because all the devices we will work on will expect to be like found in some address. The kernel we will load in the VM that is compiled for Snapdragon will instead find this ARM board address space. So of course it cannot work as easily as that. I've introduced before the DTB concept because this is basically what we will use to get our way in and get it working correctly. So you have this collision that must be handled in some way, and the DTB is the easiest way to get it working. Second problem is basically this one. So this is the representation of the Snapdragon device tree, which is way more complex than whatever you can find in like a virtual board building QEMU. They have like all these devices that you can see around. So all of these nodes are basically a device in the Snapdragon, and then all these red, like the green, the green lines are basically the links I've described before as well. So I've done some work for you. Like this is basically what you will find there. You will have a lot of different zones that contain devices that are kind of linked together. So you see you have some things dedicated to the modem, the CPU, sensors. I mean, it's very dense. Of course, we are not interested in all of this. For the GPU, if you spend some time trying to reconnect which nodes interact with each other, we can see that basically you can reduce this tree to spatial memory, RPMH, which is power management stuff, the GPU, and the GPU power levels that connect to RPMH. So now that we know exactly what we're dealing with, we'll need to build a running kernel. So now the goal is to take the Android tree of Qualcomm and get it running in a VM. So what exactly do we need to change the build system to get it working? This is more or less the changes I've done to make it work. There are some tweaks to the kernel configuration necessary to disable some things or like get them up again so that they can connect to the ARM board stuff. I will not describe everything there, but you get the idea. Like you need to remove this hypervisor thing that is not necessary for the GPU to work. KSLR, this is mostly for debugging. We remove some code that is not really necessary there. And then the init patches, the init process in Android, for example, we try to set up some SLinux rules that must be enforced. I've just removed everything there. I mean, it's mostly useless for security testing. And then what happened is practice. So you will have to go through these lovely scripts to get Android running. This is basically 4 hours of building, so each test is kind of a pain. This is an example of module you will find in the build tree. So basically you have 4 build systems interleaved that do not communicate with each other, and some of them are even incompatible. So if you modify one of these files, most likely it will do nothing or break everything, so it's also a source of problem. I've not put everything. I spent 1 month just to build things maybe 10 times. I mean, it's not very difficult, but it's a lot of time just because you will need powerful machines to build these kernels, I don't know, 20 times, but if they all take 4 hours to build, you will need some time in front of you. Then the Snapdragon integration in QEMU. I will describe there what devices exactly I've integrated, what was necessary to get the GPU stuff working. I didn't integrate all of these devices let's say at 100% features. My goal is basically to get it running, and that's all. I don't care if this single feature is missing for now. The goal is just to see, okay, what exactly do I need so that the GPU can work, or at least expect to work correctly as if it was running on the real hardware. So how did I deal with the address space collision I've mentioned before? It's very easy. Actually, I just put it below. It's not very subtle, but if you change the DTB correctly, there should be no problem. You just need to make sure that the DTB of the Snapdragon and the DTB of the ARM board can kind of merge correctly. but because the space below is free, you can just basically put it there and then just make some offset. This is what I've described there. You have this QEMU Ambient board that is built by QEMU, and the one for the Snapdragon that is a very big binary blob. You just put them together and relocate the addresses recursively, and then you get something running. Sysbus OF. This is a bit more technicalities. It's not really necessary to understand everything to get the rest of the presentation. But this is an abstraction of the devices that I made in QEMU so that they can be kind of built automatically. The idea behind is that DTB contains lots of information about devices, and I want to reuse some of them so that I don't have to do it myself. Like, what is the address of the MMIO? What is the address of the interrupt? I mean, what is the interrupt line or this kind of stuff? So the idea is just to have this middle device that is kind of generic, that will be filled automatically from the DTB, and then I can build my device above this with all this information pre-filled to save some time. And then we can go to the GPU stuff. This is a bit the things I've met while building these devices, like what are the big problems that arise when you just let the VM boot and see what happens. You will find some infinite loops because some device is expected to return some precise value. Incompatibility device found because you didn't put the right stuff in the DTB replacement. And the most annoying of them all, the kernel module deferral. So I will spend a bit more time on this one because it's really what makes this work hard, in my opinion. Like the deferral mess, as I've called it, is basically how the kernel handles the fact that some device is not ready yet. Some device will expect another device to be ready, and if it's not ready, it will sometimes return this value called the -e prob defer, that basically says, please reschedule me later on so that I can try again and see if the device is ready. The thing is, you can have this problem for many reasons. It could be because the device is missing. It could be because the device is not loaded yet. So when you are building a VM from scratch, the thing is most likely the device will be missing, and then the defer will happen. But sometimes it's just waiting for 5 minutes before the device is up, and then it's not actually a problem. And most of the time, it's completely silent. So you will basically see nothing appear in the message. So you have to take care of that kind of manually. This is how it works when the defer happens. Let's say you have like a kernel module that depends on the 4 other kernel modules with this structure. Maybe the module G will boot correctly. The second one will be deferred. The B will work correctly. Then A will be deferred as well, which will also defer the target kernel module. But then you will most likely not see C and A be deferred. You will only see that the one you want to see loaded, not loaded at all. Let's come back to this figure. What I've done is to kind of filter this figure and just keep what is the interesting part for us. So I just took the nodes in the circle you've seen, and then I've just deleted everything else. So you can see, like here, I've decoded in red the devices I've implemented. The other things are not either necessary or can be kind of ignored. But yeah, this is basically a visualization of the work I've done for that. So as before, like they're exactly the same thing. You can see the RPMH part of the right, GPU power levels, the GPU, and the spatial memory. I will just go through some devices very quickly to give you an idea of what they are doing and like what kind of stuff they expect to. I mean, I would expect them to do so that the kernel can work correctly. RPMH RSC is a device done for like power management. GPU, like they use a lot power management things to lower the voltage when they are not really used or this kind of thing. So you have a lot of interaction, so you cannot really ignore it. RPMH RSC is a protocol between a kernel module and a device that we basically like use interrupts to communicate together. So the idea is you have the guest, the guest kernel, and the RPMH device that you build yourself. You will first write a message somewhere. You have a trigger to signal to RPMH that the message is ready. Then you will have some handling, and then asynchronously you will have this interrupt going in. Usually when you see the word asynchronous, it means it will be a pain to debug. It's always like that. So you just have to make sure that the interrupt is working correctly, and then spend some time with GDB until it works. There is this SMMU thing that is the IOMMU used by the GPU. An IOMMU, to make it very simple, is the device that will map the address space as seen by the GPU with the address space used by the virtual machine, so the physical address space of the VM, in other words. And this device basically just takes care of mapping this thing together so that everything can work correctly. This is necessary because there is this device called HFI, I will present just afterwards, that basically expects this to work. So what I've done is to remove all the code of the SMMU in the kernel and replace it with this very simple IOMMU that will basically write some mapping between physical address and AOVA, which are like the device virtual addresses. You have some page size, page count, permission, VMID. This is a bit more important, less important for the understanding of this. And then you have the commits that basically say, okay, I've set up everything, take it into account now so that when the device tries to write to this address, you need to hit into this physical address. And then HFI, which works through DMA. So DMA is another word to say asynchronous memory communication. Basically, it's at the heart of the HFI protocol, so if this doesn't work, you will never see anything between the emulated GPU and the kernel. It's both asynchronous and bidirectional, so even more pain perspective. You will have this queue table that is used to communicate, this is basically your shared memory. I will not go into the technicalities there, but you have these two queues. One is used to write the message you want to send from one device to the kernel module, or vice versa. This works the same way. And then you have the second queue that will just send some ACKs so that the message can be acknowledged. So this is a more accurate list of the devices I've implemented. This is basically more or less 10K line of code. You have a list there. The repo is available, it's open source. You will have the link at the end of the presentation, so you will have some time to dig into that. This is the final overview of the virtual machine. It gets kind of complex at first sight, but if you take the time to decompose it, you can map it back to the code and then hack into it and get your own stuff working. This is a demonstration. This is the gmask of the virtual machine we are running. So basically, you can see all of these things at the beginning are basically the boot of Linux. This init line are basically the kernel modules running. So there are all the kernel modules linked to the device I've presented before. And then after some time, you will start to see the KGSL, which correspond to the GPU kernel driver, doing some tests. So what you see basically there are basically all the tests that are running to the kernel driver. If you see that, even there are some errors, it's most likely working. So from there, you can basically run anything and then see if you can find some bugs. The funny thing is that just the process of trying to emulate this GPU stuff led us to some interesting findings and this CV that will be published in January. The idea is basically that we need to read a lot of code to get this to get these devices integrated in QEMU. We read the code, we see that something looks weird, and we just find bugs. I mean, it's kind of simple in that sense that because you need to understand the kernel driver to get the device running, you will see that sometimes things are not matching, and then it can either be very harmless bugs. Most of them are harmless, and sometimes they can be more interesting, like this one. So as I said before, this bug has been reported and will be presented later on because it's still not disclosed completely yet, so it's still under embargo. But once again, with the final slide, you will see the repo in which I will say more about this CV later on when it's public. And then the fuzzing part. I have 1 minute to present it, so brace yourself, it's going to be very fast. LibAFL QEMU, so the thing I've presented at the beginning, which integrates the fuzzer and the QEMU stuff in the single process. So LibAFL and QEMU, they communicate without any shared memory or this kind of thing that you will see in many other fuzzer based on QEMU, and can communicate directly through some kind of command system that I use a lot to communicate with the VM. It has been presented 2 years ago during 3073. Since then, we have a lot of different changes, and I cannot really present them now, otherwise I will spend too much time, but basically remember there are some new cool stuff that you can find out. If you didn't take a look to that until then, maybe it's time to get another look. We had to change kickoff. The idea is that you can compile the Linux kernel with some options so that you can get the coverage as I've presented before. The problem is that kickoff doesn't give you the coverage. As I've presented at the very beginning, they have another subtly different coverage stuff. So they will just basically list all the IPs that the program will go through. IP is for instruction pointer. So basically, it will just list all the addresses at which you will go through, and it's not really compatible, at least not out of the box with LibAFL. So what we did is just to turn it into the usual coverage we use, which is also faster. And then another problem that is a bit more subtle is that virtual memory the memory is allocated through virtual memory allocation, which means the physical address space will be kind of fragmented. So what we did is just to put it through physical memory allocation, and then you just have one memcmp, so it's also faster. This is the final integration. You will be able to find the slides later on, so if you want to take some better look at this, you will be able to find it in any case. This is the final slide I mentioned, QR code to the repository with all the links and the stuff I will add later on. So take a look if you're interested in this work, please. And I think that's kind of all. There is one thing I will not be able to open source, is the fuzzing harness. This thing was impossible to get accepted, but all the rest is either available now or will become available later on. Thank you very much.
Thank you, Romain. Do we already have some questions? I see, no, that is not a move towards the microphones. Does the Signal Angel have a question from the internet? Oh, I see someone lining up at microphone 1.
Hello.
Hey.
I was wondering, is the architecture of the GPU just ARM core? Or is it hexagon? Like Qualcomm also has hexagon for many of its other stuff.
I'm not sure exactly what I can say there.
Okay.
I don't want to do a mistake, but I mean, I don't think I can reveal it, or I can't say any details. But
yeah, you are running it in QEMU, so it's
so what we are running is most the HFI layer, which is an interface between the GPU and the kernel module. So what we do is to emulate this HFI part, so that we can see whatever is going to be sent to the GPU. And then it doesn't really matter what architecture is run on the GPU, because you can just basically look at the commands that are sent and then do whatever you want to emulate these commands.
So you're not emulating the actual GPU?
Not fully, yes. We are emulating the external layers that are necessary to catch the commands sent to the GPU, and then get the GPU emulated, but it's not really, we don't emulate it perfectly. We don't emulate the microcode or whatever could be inside. But basically, we just interpret the commands that are sent to the GPU, and then we just rerun it in the host code, yes.
Okay.
Microphone 3 was next, I think.
Hi, I just wanted to ask if there are any plans to extend this work beyond the GPU. Hexagon was mentioned, but other peripherals, for example, or this for now?
Thank you for the question. So the goal of the internship was to do it with the GPU more as a way to see if it was working, because back in the time we didn't even know if it would ever boot at some point. So I'm not sure exactly what is planned in the future for that. I hope they are going to extend it with other devices. But we chose the GPU because usually it's an interesting attack surface, but there is no reason to not extend it to other things. Actually, I didn't mention it, but I've heard that Qualcomm wants to maintain this repository with all the devices that are already there, and would be happy to get some pull requests. So yeah, I hope they are going to at least continue to get new devices in.
Thanks.
Thank you.
Next up, I see that our Signal Angel has a question.
Yes, so there is a question about the hardware that is needed to run this. So do you need powerful hardware like 128 cores CPU or a dedicated GPU, or does it actually don't make a difference?
Yeah, thank you for the question. Yes and no. Of course, the more powerful the hardware is, the faster it is. The GIF you've seen with all the boot is accelerated, so it's not that fast in real life. It was done through emulation, so it's much more involving, but it should also work through virtualization, which can make things much faster without having to have more powerful hardware. And this example, I think I was using 8 cores and something like 4 gigabytes of RAM. I think it's reasonable, but I didn't test every possible combination, so I'm sure you can get it running with less resources. But because it's emulation, in this example, it's going to be slow in any case. I think the boot is around 1 minute.
Thank you. Microphone 1 again.
Yes, I was wondering if you had access to the hardware reference manuals for the GPU during your internship.
No.
Why didn't they let you access that? Because I think that's a necessary thing if you want to make a model of that device.
It's a good question, thank you. The problem with this thing is that it's very slow. Like accessing some restricted documentation or things that shouldn't be like publicly available even in the company can take a lot of time. And the internship was with 3 months also. Basically, they didn't handle the request in time, so it was just faster to reverse it by looking at the kernel than waiting for them to reply. You know how it is. Yep.
Microphone 4, please.
Yes, during fuzzing, did you find bug that ended up being in the emulation code rather than in the GPU?
Actually, yes. Most of the time, especially when you first do some fuzzing with the emulated devices, you find way more bug in your emulation than in the code you are trying to test. But usually, after some time, you are able to reduce these bugs and get something that makes more sense. But yes, most of the bugs I found first were in the emulation side.
Thanks.
Thank you.
Microphone number 3.
Thank you for the talk. I was wondering, since you just mentioned that you were running QEMU in emulation mode rather than virtualization, why did you go with KCOV for coverage rather than using the feedback from TCG?
Yeah, it's also a great question for 2 main reasons. The first one is because I plan to use it for virtualization later on. So in any case, I will have to go through this. At least it was what I expected to be the easiest way to get this feedback. The second one is because getting feedback from TCG can be a bit tricky because you will get a lot of different things that are not specially for the kernel module. I compile KCOV with some special options so that I can just get the feedback from the kernel module. So basically, if I just let it get any feedback I receive from TCG, it will be unstable, first of all, and mostly uninteresting for the feedback.
Thank you.
Thank you.
Short check with the Signal Angel. Anything from the internet? No. Then we continue on number 1, please.
Thank you for your talk. So my question has already been asked and answered, but I have a comment. So about the probe deferral stuff, in new kernels there is a function graph tracer with return value support, and that's tremendously useful. So
Awesome.
you can just search for -517 and see all the probe deferrals.
Really?
So you don't have to dig behind it yourself.
Oh, that's awesome. I hope I will have that during my internship. But yeah, what I was doing was just to do some breakpoints in the kernel and then just decompose the structures internally. But I would have preferred to go that way. It's less time consuming. Thank you.
So there have already been some questions asked about how you implemented the different devices. I'm wondering about blobs. Are there any blobs required, both for the actual emulation and also for being able to run it? And are those blobs available to people who don't dump it from their mobile and don't have an NDA with Qualcomm?
Yeah. Thank you for the question. I don't think you will need anything that is actually unavailable. I'm not completely sure because back in the time I had access to an internal repository, but as far as I know, at least this repository is available as open source, and I've seen some manufacturers like Samsung release open source package ready to compile stuff. At least I didn't need to dump anything from internal device or anything. I just took the main Android thing, build and run. It's actually requiring some binaries, but they're embedded into the build as far as I know, so I think that should work without any weird things.
Okay. Yeah, so the emulation doesn't require blobs.
Not my knowledge. You will need something in the virtual machine. It has some blobs there, but I think they are embedded into the final build artifact, so that should be fine. For the emulation, nothing at all except the DTB that you can already find in the image that is baked in build. So that's all.
Thank you.
And with that, we are out of questions and out of time. Thank you, everyone. Give him a very thundering applause.